Annyeonghaseyo, I guess I'm pronouncing it right. um, hey everyone, how's it going? I know we are in the middle of a day, and I'll try my best that I'll keep this talk short and sweet. So let's just jump right in. Now, let's take a moment to think why we choose to use certain apps. There are a few reasons why we choose few apps. Either the apps are very smooth, seamless, or like performing seamlessly. And most important, meeting user needs effectively. But what would happen if apps are dropping frames, become sluggish, or maybe like crashing in between of critical tasks? I'm pretty sure if you are a user, you may be really, really disappointed, and you might seek out alternatives. That is the small effect that could be because of your app's performance. And slowly, slowly, it will affect your app's reputation as well. So one of the reasons of this slugginess could be a memory leak. A memory leak could be likened as a small leak which is capable enough of sinking a great ship. It may look small at start, but its effect could be really, really disastrous. So, in today's talk, we'll delve into deeper what a memory leak is, what are its effects, and most important, how you can prevent it. So, fasten your seatbelts as we navigate through the treacherous waters of memory management in app development. Let's ensure that our apps stay afloat and, most important, provide an exceptional user experience. Before moving ahead, let me introduce myself. I'm Ayushi Gupta, a Firebase GDE. So you can expect something around Firebase in this talk. A WTM ambassador. So if you have any questions regarding this program, I'm around. I'm currently working as lead Android engineer at Zalando, based out of Berlin. So want to know more about my journey? You have my website, and feel free to connect with me on Twitter. So after a bit about me and my current organization, let's just start our journey to save our sinking ship. There is a saying, if you know it, you can deal with it. So why not? Let's just start with a bit of understanding around Android memory structure. Most of the apps on Android execute on the top of Android runtime, that is ART, which actually replaced Dalvik Virtual Machine, and they both have a similarity share with Java Virtual Machine. If you look deeper, ART uses two separate memory spaces to store running application and its data. These memory spaces are stack memory and heap memory, and they combiningly form a major chunk of your device RAM. But that's not enough. We have to go a bit deeper. So let's just have a wider look at stack memory. Stack memory is mostly used for the execution of a thread. So you can say it contains method-specific values, which are kind of short-lived, and even references to the other objects in the heap. So as soon as the method ends, that particular block becomes unused, and it becomes available for the next method. So you can say stack is more about static memory allocation. Stack is usually referenced as LIFO, last in, first out. So it's kind of pretty fast. Now, when we are talking about stack memory, obviously there's going to be a limit of size, right? So whenever you're going to hit that particular limit, you're going to get stack overflow error. So that's in a nutshell for stack memory. Let's just see a bit about heap memory as well. Heap memory is responsible for the dynamic memory allocation. in your entire app. So unlike stack memory, which is used just for the thread, heap is used all across your app. So whenever you create an object, it is allocated in the heap memory. And these objects are accessible globally. To ensure a seamless user experience, Android puts a hard limit on heap memory as well. If you say that the heap memory is directly dependent on the available RAM on your device, and whenever you're gonna hit that particular limit, which Android set, you're gonna get out of memory error. But that usually doesn't happen. So what's running in background? What is helping you out? So in virtual machines like JVM, DVM, or ART, there exists a superhero known as garbage collector, which primarily role is to detect and reclaim unused objects, and thereby freeing up memory space for you. Garbage collector scans the entire heap and identify objects that are unreachable. So when I say unreachable, it means that if an object in the heap does not have any references pointing to it, it will be reclaimed by garbage collector. There are various algorithms that are working under the hood in GC. There could be mark and sweep, concurrent, and generational. And they actually are helping for your improved application performance. So whenever you say any object equal to null, you're saying that, hey, GC, please collect this object. I don't need it. So that is GC for you. But that was all about your application. Now the question is, how is Android's memory managed? Let's just try to seek some answers. Android devices basically contain 3 different types of memory. There is RAM, then there comes ZRAM, and then there comes storage. If you see that CPU and GPU, they are combiningly using your RAM. So RAM is like the fastest type of memory that is available, but it's limited in size. So whenever you buy high-end devices, you choose your RAM because it's going to affect your app's performance on your phones. Then there comes ZRAM, which is a partition in the RAM. Like you could see, it's a part of the RAM. And it could grow and shrink in size. Whereas storage is kind of bigger if you see, but it's more about persistable data storage. It contains all the application, libraries, and everything which is there. It's basically inside storage. And storage has much more capacity than the other 2 types of memories. So let's just try to see how physical memory or RAM on device is organized. Physical memory or RAM is usually grouped into pages. So each page is typically around 4 kilobytes of size. And different pages could be used for different things. For example, there could be use pages. So whenever you're running any process, it's actually been part of your use pages. Then there could be cache pages. These are the pages that the processes are using, but some part of them are still present in the main memory. So here you're gonna have some fast retrieval of data. So we do have cache pages. And then we have free pages, which are like the pages of memory, which are just sitting on the device, doing nothing. So let's just have a look a bit here. So what I've done over here, I have taken a 2 gigabyte device, and I started using it. So you could see I started by doing it nothing. So at the very beginning of the start time, there is no processes not running, nothing at all. Now, I eventually start running my different apps on the device. So you could see that the free memory is dropping now, right? So that was a happy state where there's a lot of free memory available on your device. But over the time, I keep on increasing the apps that I'm getting on my phone. Then the free memory will obviously get exhausted. And to avoid very bad things from happening, now the kernel has to do something. So Linux kernel has this mechanism, which is called as kswapd. What is kswapd doing? Kswapd is going to find more free memory for your device. So it basically kicks in when your free memory drops below a threshold, what I'm calling here right now as k-swapped threshold, right? So now if an app is going to access a cache page or memory that was present on the cache page, then it's going to take a bit more time, right? So it's like an okay state to be in because the user might not notice it. But now just imagine a situation where you actually deploy more apps on your phone or you're just using a lot, right? Then the number of cache pages are also going to fall down because there is no availability of cache pages as well. And that's like a very bad thing to be in because your device will start to thrash. And it might be ending up in a situation where your device might get locked up. On Android, we have a mechanism which is called as low memory killer, which comes in this scenario. And when low memory killer comes in, it's like it's gonna pick up any process which is taking up the memory and just kill it. Now just imagine if you were using a process, let's say any app, and low memory killer kills it. I would say no one would want to be in that situation. And as a user, it's literally not recommended. So not a really, really good state to be in. If you want to know more details around this, about which process are selected or how they are selected, you can use this QR code. Okay. So now we have GC and low memory killer which are working together to manage memory in Android. The GC basically operates in your application runtime environment. I think the Wi-Fi, one moment. Okay, so the GC and the LMK, they both are trying to manage the memory on your device. GC is basically running for your apps, whereas low memory killer is running on your application. So now what low memory killer can do? It can literally go and ask the GC of your app, ki, hey dude, I want to kill this app, just clean up all the objects that have been allocated for this app. So they both are working together for the memory management on your device. Now the question comes in, if our superhero fails, what would happen in that scenario? It's time to bring the leak in picture, which is capable enough of sinking a great ship. That is a memory leak. So you can say a memory leak could be just an object whose memory was not collected because there was still a hard reference to it. In short, GC was not able to take out the trash. So when the user keeps on using your app, the heap memory keeps on increasing. So initially, what would happen? First, a short GC will come in picture. And the user might not notice it because it's around 2 milliseconds to 5 milliseconds of pause. And it runs on different thread. But let's say you have some serious memory leak issues. Then the big bro has to come in. So after short GC, we have large GC that comes in. And it will literally pause your app because it's going to block the main thread. And the pause is significant because it's 50 milliseconds to 100 milliseconds of pause. And during this point, your app seriously lags, and it almost becomes unusable. Even if this doesn't fix the problem, then the heap memory of your device will keep on increasing. And ultimately, end in a situation where your app will terminate with out-of-memory error. Now we know what a memory leak can do to your app and customer experience. Lesser the garbage collector has to execute on your app, the smoother your app will be. So why not let's just detect the memory leaks in our app as a step towards better experience? When it comes to memory leaks, developers often turn to Memory Profiler, which is integrated as a part of Android Studio, where you can actually analyze memory usage in your app. But I would say that this particular step is a proactive step. And as a developers, we usually tend to do a lot of things together. And we might do profiling, let's say later, hash never. So why not let's have something which constantly reminds you that you have a leak to fix in? My suggestion would be LeakCanary 2. We are talking about today a leak detection library that is LeakCanary 2. It's not just LeakCanary we are talking, it's LeakCanary 2. It's an upgrade that has come in, and it's much more powerful version. Since it's an upgrade, the internals have been rewritten. And now it can detect multiple leaks in one analysis. And they can be grouped per leak type. Now even we have simplified API configurations. We'll see how we can use this API configuration to detect and visualize our leaks. Not only that, they have the new Heap analyzer which is in, and in turn that has also been re-implemented from scratch. What makes LeakCanary special is the knowledge of Android fundamentals. LeakCanary gonna do these 4 steps for you when detecting memory leaks. First, it's gonna detect what are the retained objects. Then it will try to give you the data by heap dumping. Then it will go with heap analysis. And most important one is leak categorization. Let's just try to see a bit in detail around these steps. LeakCanary hooks into the Android lifecycle so that it could automatically detect when your activities and your fragments are actually getting destroyed. And it receives all those dead objects, and it passes it to Object Watcher. What does this Object Watcher is doing? It is actually holding the weak references of all those dead objects. For example, it could be the destroyed activity instances, it could be destroyed fragment instances, or maybe like whenever your view model is getting cleared, right? Not only that, they also have the APIs where you could add any object of your choice. Now, if the weak reference that was hold for 5 seconds of wait time and running GC on the top of it, it's not been cleared, then LeakCanary says that this object could be potentially leaking. What does then LeakCanary do? It maintains the count of those retained objects. It's not like that, okay, I got an object, so it must be leaking. It actually does a bit of analysis over here. It keeps the count of the retained objects. The threshold that we have over here is 5 when your app is in foreground. And when your app goes in background, that particular threshold is automatically set to 1. Now, as soon as the count crosses the threshold, it initiates the heap dump. I guess you all know this toast that comes in when you're using LeakCanary. So what's happening over here? It is actually dumping the entire Java heap into a .hprof file, which is then stored in your file system if you want to read it. And during that particular process, you're going to see this toast. Then let's talk about heap analysis. Now you have all the data that you want. So LeakCanary going to parse it using Shark. What is Shark? Shark is Smart Heap Analysis Reports for Kotlin, which itself is a new standalone library now. Shark gonna detect all the retained objects that were there in that particular hprof file. Then it will go to the path references of those retained objects, like what it actually led it to the state where it has been right now. Not only that, LeakCanary creates signature for each leak trace and groups them together so that maybe it's easy for you to find a bug, right? If you have a closer look at the leak trace, it looks majorly like this, which is the hash of the concatenation of entire reference that an object was using and might be a reason of leaking. Even they have the concept of using underlines to tell you, yes, this could be a suspicious one. Now let's talk about categorizing leaks. I guess everyone is using libraries in their Android apps. Is there someone who is not using libraries in their code base? Come on, guys, I can have a yes or no. Are you guys not using libraries in your code base? Okay, that's a very silent audience, to be honest. Okay, so LeakCanary have categorization of application leaks and library leaks. So whenever you're using libraries in your code base, they could be also leaking, right? So fixing it may be out of control. So LeakCanary extracts it out. And what you need over here right now is application leaks, which are majorly coming from your code base. So now you have seen all the capabilities of LeakCanary. Let's just see how we can add it into our code base. These are the simple dependencies that can add LeakCanary into your code base. If you notice over here, we have debug implementation. We have release implementations as well. So when we are talking about debug implementations, it will not have any referencing in release builds. Now, you just see that the dependencies are also quite linear. You don't have any referencing to any other things. It does not depend on Android X either. Not only that, detection of Android X fragment is now automatic. So when we are talking about release implementation, I would say this is a state which is experimental as of now. But still, it's worth reading of the data that we receive in our release builds. OK, so any feature development is not completed until you have added testing to it. So LeakCanary even assures that. So we do have now test dependencies for LeakCanary 2. It now has an artifact that you can use in your UI testing cycle, so that during your testing phase itself, you can detect leaks. The dependency is quite simple as you see it. So if we talk about adding it to our code base in testing phase, you just need to add leak assertions.assert no leak in your test cases. So what it will do, it will trigger the same mechanism that we have seen, right? And at any point, it will check for leaks. Let's say if retained objects are detected, then LeakCanary will dump and analyze the heap. And let's say if the application leaks are found, then your test will fail with the error as no leak assertion failed error. But I would say, does it even make sense to write leak assertions.assert no leak in a test file which has a lot of test cases? Let's say you have a testing file, let's say with 10, 20 test cases, sorry. Then in that scenario, you would not like to write that. So we do have rules now. You can use this rule, and it will automatically execute the same code after every test. Let's say you're working on fixing a leak. So in that scenario, you would like to make sure that the tests are executed smoothly. So you can now have this annotation in your tests. If you add this annotation, we will not execute the particular leak test on that particular piece of code. So it's all sorted. Now we have all our tools ready. It's time for the quest of cleanup. But before we take a step ahead, I want to talk around how a developer strategy looks like. Usually, you start development, you get a product requirement, and you start working on it. Maybe once your building is completed, you would do manual testing or, let's say, automated testing, and then raise your PR and get your code merged. Then in this journey, as a developer, you will be very rarely going to go and check what the LeakCanary logs are having in your feature development cycle. So why not let's do something to wire it in our development cycle itself? As I was talking about, that LeakCanary 2 has new simplified APIs which give access to the heap analysis process. Why not let's use it? Let's implement a listener to heap analysis process. So what I'm talking about right now is adding an event listener to the heap analysis process. Whenever the heap analysis success, I'm going to use that particular piece of data with my upload service and going to upload it. But before doing that, you have to add it to the LeakCanary config. And I guess this is going to help you out over here. But before we move ahead, be have your eyes on your LeakCanary upload service. What does LeakCanary upload service do like? So LeakCanary upload service gonna do the proper extraction of the heap analysis success data class. We will extract out library leaks and application leaks data separately. And you can transform it the way you like, but make sure that you preserve the data format. What I'm going to use over here is the custom stack trace builder so that whenever I'm reading that particular data, it's in a proper format. But now the question arises, where I should visualize this quite a big chunk of data. I want something which is kind of real time, where I could check how many developers are facing it. And most importantly, I don't want to add any more dependency in my code base. So why not use Firebase Crashlytics? Firebase Crashlytics is currently part of most of the Android apps. So why not use it for visualization of leak traces as well? It's pretty lightweight. Almost a real-time crash reporter. You can easily track what's happening. Not only that, you can easily track what's happening on what device, and even you can have additional info. There are options to add additional capabilities in it. And you can see the number of developers who are getting affected by that particular leak trace. So quite easy prioritization to fix those stability issues. So now, let's just wire our LeakCanary upload service with Firebase Crashlytics. What I'm going to do over here, I'm going to log it as non-fatal exceptions because I don't want to affect the production numbers. You can track affected users. Then I'm going to have the categorization so that I know what are the leaks that are coming from libraries and from my own code base. And then I can easily prioritize it. So if you talk about the code, it looks something like this. So this is the capture heap analysis that I have, and then I'm going to play with it, and I'm going to use it like crashlytics.record exception and have a non-fatal exception logged in. So when you try to visualize it on your Firebase Crashlytics, you could see the entire information on your Firebase Crashlytics now. And you could just read it in the same data format that you had earlier. If you recall that we were having a conversation around having the LeakCanary 2 in your testing phase. So why not have leak assertions.assert no leak into a testing cycle as well? So this is what you can add in your testing cycle as well. So this will help you to detect and upload the heap analysis report for your testing phase to the Firebase Crashlytics. This functionality will actually help you to detect vulnerabilities in your testing. So when you're running your test on CI/CD, automatically everything will be tracked on Firebase Crashlytics. I guess that's cool enough. And one more thing. So when we are talking about Firebase, we have a tool ready with all set of information. Let's just have a few more integrations when we are using Firebase Crashlytics. Let's have Jira ticketing done whenever you have, let's say, crashes crossing a particular threshold. You can go ahead and create Jira tickets automatically now. Then comes Slack integration. I guess most of you here would be using Slack. So you can have the alerting system set up for your crashes, which are coming through your memory leak now. Just a tip over here, when you do this, you need to use new non-fatal issue payload because you have logged your crashes as non-fatal exceptions. If you need more information on this, do check out the official documentation page. I guess this is what remains. Let's just try to fix the leaks. Memory leaks gonna cost you a lot in terms of your app performance and in turn, user retention too. So here are some do's and don'ts that you can incorporate in your coding style to avoid leaks. I'm not gonna go one by one in each of it, but yeah, this could help you a bit. I guess development is an ever-going journey, But these small steps, while building the app, can help you to deliver your high-performance Android apps. Detecting, visualizing, and fixing memory leaks will not only make your app's performance, like app's user experience better, but it will slowly turn you into a better developer as well. Leak detection can tell you when there is a code smell, or let's say bad coding patterns, before they get baked into your code base so much that you literally haunt, like you feel that, hey, it's very, very tough to fix it. Leak detection can teach developers to write more robust apps, making sure that you're taking care of low-end device users as well and giving them the same user experience. No doubt, development is an ever-going-on journey, but these small things can help you to save your ship from sinking and can set the course of selling it high. This is some food for thought before we wrap up the session for today. And so let's give this session a wrap for today. Thank you, everyone, for being patient listeners. I guess I do justice to my trip in Korea. Gam Shabanita.